Hello, and welcome to the California State University of Los Angeles Spring 2021 Solar Demonstration Lab, instructed by Professor Michael Thorburn and advised by Professor Samuel Landsberger. Our team is broken up into four subdivisions. Team 1 consists of Calvin Chhun, Mohammed Shukr, and Nathan Castro leading the solar panel tracker team. Team 2 consists of Ashley Gu, Faisal, Aldossari, Ulises, Vega, Peralta, leading the solar hot water team. Team 3 consists of Alex Rodriguez, Kailen Loualhati, Napat, Atikanit, leading the energy analysis side, and Team 4 consists of Sergio, Miranda, and Stephen Garcia, involved in 3D printing. As a group, our goal is to research, design, build, and demonstrate a solar photovoltaic system, as well as share information about sustainable solar energy with the Cal State community and the surrounding East LA community, from schools to community leaders.
Hello, my name is Nathan Castro, and I'll be introducing the solar panel tracker section done by Team 1, including Calvin and Mohammed. So to begin, I want to describe the fundamental ideas that give us a way to track the sun's trajectory across our sky. And the first fundamental idea is knowing how our Earth rotates around the sun. And so our Earth has an axis, and it's tilted, and that is the tilt is at approximately 23.5 degrees, and that is relative to the Earth's orbit around the sun. And so for the northern hemisphere, the summer solstice is the longest day of the year, and that is because the Earth's axis is tilted the most towards the sun. At the autumnal and vernal equinoxes, the Earth's axis is sideways to the sun. So you can think of the sun rays hitting the Earth at a perpendicular angle to its axis. And then finally, at the winter solstice, the Earth's axis is tilted the farthest away from the sun. So here we have a picture of a home at a fixed position and this sort of sky dome. And so the first path you see there is at June 21st. And that is the summer solstice. That represents the summer solstice. And that's the longest path that the sun is going to take throughout the year. And then below it at December 21st represents the winter solstice path. And that is the shortest path of the year. And again, that is because at the summer solstice, the axis is tilted most towards the sun. So that makes the sun stay in the sky a lot longer. Whereas during the winter solstice, the axis is tilted away from the sun, causing the sun's trajectory on the sky to be the shortest. And so throughout the year, the sun's path will always be between the summer solstice path and the winter solstice path. So in this picture, there's a line at 3 p.m. and there's a line at 9 a.m. And so on that line at 3 p.m., the sun will always be on that line at 3 p.m. throughout the year, in between the summer solstice path and the winter solstice path. And the same thing for the 9 a.m. line. So there are two important angles that we use to map the sun's motion through our sky. And the first important angle is called the azimuth. And from a fixed position, the azimuth is the angular measurement that gives the direction or heading of a celestial body. And in our case, the celestial body is going to be the sun. And basically, so you start at the center of the circle, and true north is going to be 0 degrees. East is going to be 90 degrees, south is going to be 180 degrees, and west is going to be at 270 degrees. So depending on where the sun is on that circle, you'll get your azimuth angle. The second important angle is called the altitude, and it's also referred to as the elevation angle. And the altitude or the elevation angle of an object is its vertical angular elevation above the horizon. So if we want to theoretically estimate the sun's elevation at the equinox, the summer solstice, and the winter solstice, there's two main assumptions that you need to start with. And the first is knowing your latitude at the area you're at. So for Los Angeles, our latitude is approximately 34 degrees. And the second thing you need to go with is that, as I mentioned earlier, during the equinox, the Earth's axis is at a perpendicular angle to the direction of the sunlight. So we have a drawing here of the Earth, and then there's a line. So the latitude at 34 degrees takes us to the surface where Los Angeles should be, and this tangent line here represents the surface. And then this yellow line here is going to be the solar ray at the equinox. And so the tangent line, the surface line, and the longitude line create a 90-degree angle. And if the solar ray at the equinox comes in perpendicular to our axis, it'll create, through some geometry, we find that the elevation at the solar ray at the equinox of the solar ray at the equinox should be 56 degrees. And so now that we have the solar elevation at the equinox, to find the summer solstice elevation and the winter solstice elevation, we use the fact that the Earth's axis is tilted at 23.5 degrees relative to its motion around the sun. So at the summer solstice, the elevation should be the equinox elevation, 56 degrees, plus that 23.5 degrees, which gives us an estimated elevation of 79.5 degrees at the summer solstice. And similarly, at the winter solstice, it should be the elevation at the equinox, 56 degrees, minus the 23.5 degrees. So it's estimated that the solar elevation at the winter solstice should be about 32.5 degrees. And here we have a generated solar chart. So this basically describes the sun's motion or path throughout our sky on a 2D graph. And so this solar chart was generated for the LA area. So the latitude is 34.05 degrees and the longitude is minus 118.2. And at the x-axis we have the solar azimuth, right? So if we set our panel facing south, so facing 180 degrees, this would be how the motion of the sun is. And the y-axis is going to be our solar elevation. And this the very top blue line, that line is our summer solstice. And there's a little date there, June 21st. So that's our sun's trajectory during the summer solstice. So if you start at the bottom left corner, so on the summer solstice, the sun rises at an azimuth of 60 degrees. So that's about a northeast direction. And as the day progresses, when we get to noon, the sun is directly above our head if we're facing south. And then as the evening comes and the sun sets at an angle, or azimuth angle of 300 degrees. And the very bottom blue line, that line represents the winter solstice, the sun's path during the winter solstice. And then in the middle, the September 22nd line, that is the sun's path during the solar equinoxes. And so if you check the chart at noon, when the sun is directly overhead, we see at our summer solstice, the solar elevation is about 79.5 degrees. So that's what we predicted. And at the equinox, at noon, the solar elevation is at about 56 degrees, again, just as we predicted. And finally, at the winter solstice at noon, the solar elevation it's about 32.5 degrees, again, just as we predicted. So so that kind of confirms our theoretical calculations. So now that we have an idea of how the sun trajects through our sky, and we know its elevations at different times, I want to talk about the solar constant and the cosine effect. So what the solar constant is it's a flux density of the solar radiation per unit area. So basically that is just the amount of solar power going through an area. And the solar constant is measured on surfaces that are perpendicular to solar rays. And on our surface on Earth, our solar constant is going to be 1,000 watts per meter squared. So if you're going to put a panel at a fixed position, facing 180 degrees south, at noon, if you put your solar panel at the same angle as your latitude, so for us in Los Angeles, that's 34 degrees, at noon on the solar equinox, you're going to have solar rays hitting that panel at a 90-degree angle. So you're getting the maximum amount of solar power because it is at a 90-degree angle of the solar rays. And as the elevation rises or falls during the year, so at the summer solstice it rises to the highest, and at the winter solstice it lowers to the lowest, you're not actually getting all of the solar power that you can get. You're only getting the component of solar power, the solar power from the component of the solar ray that is perpendicular to that solar panel. And so that is known as the cosine effect. And so here is a little equation where we can predict the maximum power that we are able to get at different elevations. And this is all assuming the time is at noon and our panel is facing 180 degrees south, and it is elevated, and our panel is oriented at 34 degrees. So to calculate the maximum power, it's going to be our efficiency times the solar constant times the cosine of 56 degrees minus our solar elevation times the area of our solar panel. So at our summer solstice, our elevation at noon is at 79.5 degrees. And if you plug that in and also plug in the area, so for our solar panels that we have for our home kits, the area is roughly 0.286 meters squared. So you plug that all in, and we get, during the summer solstice, the maximum power is going to be 263 watts times the efficiency of our panel. And at the winter solstice, same thing. You plug in the sun elevation. At this time, it's noon, so 32.5 degrees, and we get a maximum power of 263 watts times the efficiency. And so you lose a little bit of power because of this cosine effect, and that the fact that the solar constant is measured on a surface as perpendicular to its solar rays. So this is why solar tracking becomes important, because if you can move your panel to follow the elevation of the rays or the azimuth of your sun as it moves through the sky, and you can keep that angle of incidence at 90 degrees, so you can keep the rays hitting the panel at 90 degrees throughout the entire year, you can maximize the amount of power that you get. And so Calvin is going to introduce the next slide, and he's going to talk more about solar tracking and solar tracking systems.
Hello, Professor Thorburn, Dr. Landsberger, and our audience. my name is Chhun. Today I'm presenting about solar tracking system. Solar tracker is a system that helps position solar panels at an angle relative to the sun, so that they can remain perpendicular to the sun rays. By keeping it perpendicular to the sun, sunlight could cover solar panel fully and longer, and also they would be less light reflected. In other words, the more sunlight is absorbed, so therefore it can be converted to more energy. Why should we have solar tracker? Solar tracker provides significant power output, which it can be increased about 30 to 40% over a traditional solar system. For example, we know that the sun always moves from east to west. As we can see the picture on the bottom right, we can tell the sun moves from right to left, and the picture about that is represent how we can see the sun during the highest point. In order to get most of the full sunlight to the solar panel, we want solar panel to follow the sun. So we need a way to help adjust the position of solar panel as the sun moves. In addition to that, sun angle changes north to south seasonally. So in order to track the sun from north to south, east to west, therefore we need a dual axis tracker. Solar tracker is a good way to get more free energy. However, it also has its disadvantages. Solar tracker requires one or more motors to move the panel, and this more moving part increase the installation cost, reduce the reliability. An active solar tracking system also uses a small amount of energy, and computer-based solar trackers are more expensive, require additional maintenance over time, and become obsolete much faster. Since they also use the electronic component, this electronic part may be difficult to be replaced over time. Solar tracking uses complex instruments such as computers, sensors, and motors to determine the location of the sun and to be aligned to the sun. The use of sensor can provide feedback information to the computer about the sun, so that the computer can process complicated algorithms that enable model to follow and track the sunlight. Therefore, our team decided to create a small version of solar tracker using Arduino processor to guide the panel. Building a solar tracker will help the team to experience the difference between tracking system and a fixed system. Therefore, we will know whether if we should include solar tracker to our main prototype. During the process of building the solar tracking, we design the component and test the code on Tinkercad.com visually to see if the Arduino could compile the code. Without getting any error, we proceed by building a test model. After testing the model to see if it's working properly, we began to collect data, which will be done by next week. As you can see the left side of the picture, there's a design of the electronic part with Arduino on the Tinkercad.com, which it can be adjusted and edited virtually and programming. And the right side also is a prototype that we made. It's a small model of solar tracker with components that we use from the design that we had, and also the code that we created compiled with the Arduino. And the bottom right is just a plain solar panel which will be used to compare the rate of power produced with the solar tracker. And the next slide will be introduced by Mohammed.
Solar concentrated system. Solar concentrated system collect the sunlight to produce a very high temperature head in order to generate some electricity. All the solar power systems have solar concentrated system with two main components that reflect and focus the sunlight into a receiver. Most of the systems have a heat transfer fluid circulated and heated in this receiver and produce steam. The steam turns to mechanical energy to produce electricity. Also, solar power system has a tracking system to ensure that the receiver receives high sunlight throughout the day as the sun keeps changing positions in the sky. The thermal energy concentrated in solar concentrated system plant can be used to produce electricity, and it can also be stored to use it during the day and night. Types of solar concentrated system. There are many different types of solar concentrated system, and today we will be focusing on the main four systems that many companies are using. First is the central receiver. Second is the linear Fresnel reflector. Third is the parabolic Trough. Lastly is the parabolic dish. Central receiver system. Central receiver system is a receiver located on top of a tower to receive energy from the flat distributed mirror, or it called heliostats. The mirrors are placed around the tower. The sun's energy is transferred to a fluid. Water, air, liquid, metal, and molten salt have been used. This fluid is then pumped to a heat exchanger or directly to a turbine generator. Linear Fresnel reflector. Linear Fresnel reflector, or IFR, is a reflector that concentrates sunlight and sends it to the receiver that is located above the mirror. Curved mirrors are used for a system to reflect the sunlight and downward facing linear receiver. The operating temperature is between 50 degrees Celsius and 300 degrees Celsius. The concentration ratio is about 10 to 40. Parabolic Trough reflector, or PTR, are made by bending a sheet of polished aluminum that is reflective, and it's called a parabola shape. The parabolic Trough reflector can generate much high temperature more efficiently than a single flat plate collector. The concentrated sunlight can generate a very high pressure steam for direct use in power generation and industrial steam application, and it boils water. The parabolic Trough system is a very common option for the use in hybrid combined cycle due to its mutual and low price. The operating temperature is about 550 degrees Celsius to 1020 degrees Celsius. Parabolic dish. Parabolic dish uses a mirror dish which is similar to satellite dish or even larger. It's used to reduce costs. The mirror dish is made of small little flat mirrors. Parabolic dish is the most expensive system and the least mature concentrating solar thermal collector. The operating temperature of the system is over 1800 K. The ratio is between 1000 and 5000 K.
Thanks, team, and hello everyone. We are team number 2, which talks about the solar hot water system. My name is Faisal. With me will be Ashley and Ulises. In the next slides, we will be engaging in the background of the system, the benefits of using it, show some concept and design, calculation and analysis, and then test runs and errors.
In this slide, I will be going over the components of our solar hot water system. So in the figure to the left, the manifold is an insulated box containing the header pipe. Then the evacuated tubes are glass tubes that surround the heating pipe. The figure on the right is a detailed image of the evacuated tubes. The evacuated tubes consist of end rubber caps, absorber coating, clear outer tube, heat transfer fin, top spring and plate, and the heat pipe bulb. In further slides, we will be showing how this solar hot water system functions. Here, figure 2 shows the emissions of carbon dioxide by sources from 2009. Petroleum is the leading carbon dioxide pollutant. The figure to the right shows the U.S. primary energy consumption by energy source from 2019. The leading sources are petroleum and natural gas. It is evident that the leading sources of energy consumption come from the high-yielding pollutants, that is, petroleum and natural gas. Renewable energy or alternate energy is a clean source of energy. Our goal is to promote alternate energy and make young minds aware of alternate forms of energy. The figure shows the United States energy consumption by major sources. It is evident that renewable energy has become popular over the years. Renewable energy has increased from 1950 to 2015 slightly. The goal is to eventually renewables be the leading source of energy.
Here, as you can see, is a design or a concept of the evacuated tube solar hot water system. Inside each glass tube, a flat or a curved aluminum or copper fin is attached to a metal heat pipe running through the inner tube. The fin is covered with a selective coating that transfers heat to the fluid that is circulating through the pipe. This sealed copper heat pipe transfers the solar heat via convection of its internal heat transfer fluid to a copper manifold within the header tank. These copper pipes are all connected to a common manifold, which is then connected to a storage tank, thus heating the hot water during the day. The hot water can then be used at night or the next day due to the insulating properties of the tank.
The efficiency for a solar collector is expressed as efficiency equal to heat energy coming out over heat energy coming in. The total heat power coming out is equal to efficiency of the sun multiplying power coming in from the sun. Then heat energy in is equal to the change of temperature multiplying the total heat power. And heat energy out, Q out, is equal to mass of the fluid times the specific heat of the fluid times the change of the temperature. Similarly, the solar collector efficiency for a flat plate would be expressed as heat flux absorbed by the collector also known as the actual energy into working fluid, divided by the maximum radiation energy available. Moving on to the assembly, we have our 12-volt water pump powered by our mini solar model on the left, which is hooked up to our evacuated tube hot water system ready for testing.
After putting together the solar mini model, we went to try out our first test run. We turned our water heat pump on and put it in the cooler, which had 1 gallon of water. The initial water temperature was 25.9 Celsius. After 1 hour had passed, we came again to test the temperature and found that the final temperature was 32.8 Celsius. It was a little hot on that day of the first test run. After doing the first test run, we needed another test run to get more data. So we tested on another day. And on that day, the weather was almost similar to the first run's day. It was a little hot, but with a cold wind here and there, and less sunlight compared to the first run. Because of these extra factors, the temperature fluctuated and went up and down every 10 minutes for 3 hours, as you can see in the chart. We started by getting initial temperature of 26.5 Celsius, and after 3 hours of taking data, we ended up with a final temperature of 30.2 Celsius.
Through our trials and error, we learned that the storing water unit cooler is not fully insulated. Also, the sunlight varies due to clouds covering the sunlight, which will change the efficiency of solar hot water system. The solar hot water system had some water that was also leaking out of the system, which will affect the data since the mass will change in the system.
This is Team 3. My name is Kailen, and I'm working with Napat and Alex on the charging system and energy analysis portion of the solar design project.
Hi, this is Napat speaking. I would like to go over a little bit about the background of solar energy in general. Believe it or not, solar power energy has come a long way. From the ancient way of focusing the sunlight from magnifying glass or a mirror to the modern day method of utilizing photovoltaic reaction to convert the dark sunlight into electrical energy. Solar power has advanced so much in this past century thanks to the better understanding and better leap project importance. There is a few key things that is really important for our solar power trailer. We need to be mindful of how much power it can generate, store, and be used. First thing, we need to estimate the power that can be generated in one day, and we need to acknowledge the minimum power for the battery to maintain a good health. We also need to estimate the power consumption by our appliance that we plan to be used in this trailer.
Have you ever seen homes with solar panels mounted on the roof and thought, wow, their house runs on solar power? Well, it does. And although solar panels are a great indicator for determining whether a house utilizes a solar power system, there are other components as equally beneficial to the system that is allowing you to binge your favorite show, zoom in your favorite class, and save you money. The four main components to a solar system include the solar panels, inverters, solar module racking, and solar batteries. Solar panels consist of photovoltaic cells that absorb and convert sunlight into a DC current. To start, most photovoltaic cells are made up of different layers of silicon. These layers form a PN junction, which is held together by 4 strong covalent bonds. The positive end carries extra electrons, and the negative end carries excess holes. When sunlight comes into contact with these solar cells, the electrons and holes get pushed back to opposite ends of the junction due to the electric field. This phenomenon creates a flow in charge, thus producing an electrical current. When wires are connected, the electrical current can flow into another device. Here we have a few components used in our mini model. First, we have a power inverter, the GLU 300 watt power inverter that inputs a 12 volt DC current and outputs a 110 volt AC current within a 10% range. Our solar battery is a Mighty Max 12 volt 18 amp per hour lead acid rechargeable battery.
This is our circuit diagrams of our solar panel units. We will have the solar panel connected to the charge controller. This charge controller also connected to the battery, to multimeter, to inverter, and then the inverter connected to the load, also to the shunt resistance. This means that the solar power that got generated from the panel will go through the charge controller, and we can reroute that energy to the battery to be stored, or through the inverter to be used as the AC. The inverter then will send the energy through the load.
Collage of photos of equipment we used in our mini models and lines up with our circuit diagram. To start, we have the solar panels that converts sunlight into a DC current. That current flows to the solar charge controller that feeds power to our solar battery, our solar inverter, and our shunt. Once inverted, we measure our power through the power monitor on the bottom right. With that data, we are able to analyze how much power our system is absorbing, storing, and we can tell whether there is a fault in our system. Here is the energy analysis portion. To estimate the electricity generated in an output of a photovoltaic system, we have the following equation. Energy, E, in kilowatt per hour, equals the area in meters squared multiplied by R, which is the solar panel's yield percentage, multiplied by H, which is the annual average solar radiation on the tilted panels, multiplied by performance ratio, PR. Performance ratio will experience losses due to inverter, AC/DC cables, dirt and particles between the face of the panels, shade, and temperature variations that include overcast, storm, nighttime, etc.
Hello everyone, this is Alex. Thank you, Kailen, for your part on the energy analysis. Here, we will be discussing the power consumption side of our assignment. When looking at our proposed appliances for the solar trailer, we use the following equation to determine their cost. Daily cost is equal to wattage in unit milliwatts times usage per day in unit hours times energy cost in unit cents per kilowatt hour. A short example of this can be an appliance operates at 1500 watts for 3 hours a day. The utility charges 10 cents per kilowatt hour. To determine this appliance's daily energy cost, we would first divide the 1500 watts by 1000, then multiply this value by the 3 hours of operation per day, and then finally multiply this value by the utility's predetermined price per kilowatt hour. Note we divide the 1500 watts by 1000 to account for the utility charging in kilowatt instead of watt. So now, how can we use this formula to determine our appliance costs? Well, wattage can typically be found in a product's description or spec sheet. Usage per day can be estimated or observed by a power meter. And lastly, energy cost varies by region, so we went ahead and used the national average of 12 cents per kilowatt hour. Now, let's talk about some of the devices we would have liked to see in our final build. Our original inspiration for the solar trailer was to retrofit it and make it suitable for camping or a quick getaway. When thinking of devices that could come in handy camping, we boiled down our essential list to a stove for cooking, a toaster for a quick meal, a mini fridge for any perishable goods, a coffee maker for those early mornings, a television for relaxing after a long day of adventuring, a microwave for more quick snacks, and lastly a heat pump unit to help set your desired temperature for wherever you are staying. Though we looked at several brands for each device, we narrowed it down to our top 2 contenders for the presentation, for most categories at least, just to keep things efficient. When looking at our options, some criteria we were keeping in mind were dimensions, as space on the trailer was limited, weight, as structural integrity was a concern, price, as we were on a budget, and of course wattage, as we wanted to be as energy efficient as possible. We did our best to find this data, then estimated our daily use, and then calculated daily and monthly energy costs per appliance, per the previous slide. Note the estimated daily hours may be high, but we wanted to prepare for a high energy demand scenario and have plenty of power, as opposed to keeping usage low and then being unprepared for the actual energy demand. Upon completing our appliance characteristic chart, we took this data to a design decision matrix where we ultimately looked at criteria such as size, weight, cost, availability, customer reviews, and energy consumption for each device. We then graded these appliances on a scale of 1 to 5, 1 being low, 5 being high. We then added up these final scores and selected what we felt would best fit our design for the solar trailer. We selected the Techwood stove, the wall toaster, the Yuhomi mini fridge, the Farberware coffee maker, TCL television, Amazon Basics microwave, and Senville's heat pump. From these selections and previous characteristic chart, our monthly energy cost was approximately $97.58. While this may seem high, we again are compensating for a high energy demand. The total appliance cost was approximately $1,576. By approximation and appropriate usage, this solar trailer would essentially pay itself off after 16 months of use. We felt this was important to add, as while our focus was to promote the ease and need of going green, we also wanted to incentivize the financial benefits of using solar power. Next, we have our section on K-12 engagement and interaction. Our objectives here were to demonstrate how easy using solar power can be, to demonstrate the number of appliances that can be powered, to make the case that solar is a viable option, and of course to make the overall learning experience engaging and fun for all grades. Here's a very quick overview of some projects we came up with. For grades K through 6, we thought a simple project where these students can generate power using a simple hand crank would be very fun and easy to provide for them. For our junior hires in grades 7 through 8, we thought giving them a large sheet of appliances they might use daily, along with their energy consumption, would be fun, as they could see and then select which ones they liked and felt they needed the most in their daily lives. And last but not least, for our high school students in grades 9 through 12, we thought they would be more than capable, under some supervision, to create a circuit to power their phones. And we thought this would be interesting, as these high school students would really learn and observe the size of a circuit needed and how much power is needed to power and charge their devices. With these projects, here's a bit of our vision and our hope for the takeaway result for these local students when learning more about our senior design project. For grades K through 6, we hope they would have fun using the hand crank, but then we would also hope to distinguish the difference between both passive and active power generation, and of course explain the pros and cons of both. For grades 7 through 8, we felt their project of selecting their own desired appliances would not only be interesting to see which appliances they valued most, but we would also hope to discuss the topic of phantom energy and its negative impacts. For our high school students, not only are circuits fun to construct, but our hope is they would walk away with a bit of an idea of how much power it actually takes to charge your phone, and also give them a bit of troubleshooting experience, as the more complex the circuits, the less likely it is to work the first time around. Most importantly, we wanted to spark creativity, inspiration, and an eagerness to learn about the real world around them. Maybe some of these students would eventually become engineers who we will one day entrust to safely and responsibly provide resources for us once we are older.
During the fall semester, we had the opportunity to learn SolidWorks to develop a few designs for our solar panel prototype. Here are a couple of those designs. We have the mobile solar powered trailer with a few solar panels on top.
Thank you, Alex and team. My name is Steven Garcia, and my teammate's name is Sergio Miranda. We are the 3D printing and applications team. In the next couple slides, we'll be showing you our progress using the 3D printer, as well as how we use the printed parts in our individual solar model. Last semester, our plan was to design, build, and demonstrate a trailer equipped with a solar photovoltaic system. Due to COVID, our plans changed. But thanks to Dr. Landsberger, Dr. Thorburn, and Evelyn Lee, we were able to get to work with 2 3D printers. Sergio and I were focused on learning about 3D printing and the safety protocols that one must take when working with resin. The 2 pictures on the bottom of this slide show a preview of the solar models that we have created. On the next couple slides, Sergio will be discussing resin 3D printing as well as showing his solar model in more detail.
Resin 3D printing. As Steven has said, our team focused on 3D printing, and the printer that we used was the Igloo Mars 2 Pro, as shown on the left. This printer is a liquid resin 3D printer. We used it to build and design parts for our mini solar panel system. So the advantages of 3D printing are that you can prototype parts fast when designed on SolidWorks or AutoCAD. The STL file can then be uploaded into a slicer program that will change the STL file into a G-code, allowing the printer to print the file. This 3D printer technology is a little different than your ordinary 3D printer. Liquid resin 3D printers have higher resolution, which means better detail. It is greater detail because it uses stereolithograph technology. You can see the picture to your right showing a printer printing layer by layer. It will project an image, and each layer it will cure with a UV light till eventually you see an object. Print times can take anywhere between 1 hour to 10 hours depending on how big the part is. Once the 3D printer is fully printed, it can then be removed from the build plate. If the part isn't removed carefully from the build plate, the part can crack when removing. Once it is removed from the build plate, the part needs to be cleaned with rubbing alcohol to remove any leftover liquid resin. Once the part is cleaned with rubbing alcohol, it can then be cured in sunlight or UV light. And the reason for this is so the part can gain its full strength. If the part isn't cured correctly, it can be hazardous if it makes contact with your skin. 3D print manufacturing. Here we have an example of the parts that we can print with our 3D printer. You can see a solar panel mount on the top left image that can go in the X and Y direction. You can see to the top right image has 4 parts. Those 4 parts are for an Arduino with servos that can be programmed to track the sun with a small solar panel. At the bottom you can see a multimeter and a shunt housed by a 3D part. These parts took on average of 8 hours each to print. The team has a total of 50 plus hours of experience printing tools, screws, handles, and much more. Anything designed on SolidWorks can be printed as long as it fits in the dimensions of the build plate. Here we have an image of a solar box that I built and designed. The solar box is 10 by 12 by 12 inches with a total weight of 26.2 pounds. When using the 3D printer, I was able to print out parts for this system, and the parts that were used for this system were a 2-axis solar panel bracket, a shunt mount, and a door handle. When using the solar panel system, I was able to generate a total of 163 watts per hour in real-world energy usage, amounting to anywhere between 13 amp hours. The table at the bottom is for a solar panel system charging rate. On a cloudy day, the system was able to generate 0.0025 volts per minute, and on a sunny day it was able to generate 0.0172 volts per minute. The result in the solar panel system was able to produce 7 times more power on a sunny day than on a cloudy day. Now I hand it over to my teammate Steven and the solar panel system that he built and designed.
Thanks, Sergio. This is the demonstration model that I have designed and built, which I call the solar cart. It is a box made using 1/2-inch plywood. The top of the box is secured with a metal hinge so that it can be opened and closed. The box has a height of 12 inches, width of 13 inches, length of 12.5 inches, and a total weight of 27.8 pounds when the panel is attached. On the left, you will see the wheels were attached to the bottom of the box, and on the right you will see the locking mechanism for the 35-inch long bar made of 1/2-inch plywood that is used to pull the box to the next destination. The top of the box has a resin 3D printed mounting system that can be adjusted to different angles. As seen on the right, the mounting system is secured with 3D printed screws and wing nuts. The solar panel is attached to the mounting system using extra strength Velcro so that it can be removed when not in use. When the box is opened, you will see the multimeter is facing you. The case the multimeter and shunt are housed in was 3D printed as well. The multimeter measures the voltage in volts, the current in amps, the power in watts, and the energy in watt hours. The device facing away from the viewer when opened is the charge controller, and it regulates the voltage and the current coming from the solar panels going to the battery. I wanted to know how fast the solar panels could charge the battery, so I collected data by draining the battery to about 12.5 volts by turning on the inverter and charging my phone. Then I would turn off the inverter and come back to record the measurements seen on the multimeter until about 13.5 volts. On a cloudy day, I can charge the battery at about 0.0076 volts per minute and about 0.079 volts per minute on a sunny day. This charge rate varies depending on the intensity of the sun. In the future, we would like to demonstrate our solar models to nearby schools and neighborhoods. Our solar model will not only act as a charging station, but as an educational tool to teach about solar power and sustainability.
This concludes our presentation. I would like to give a special thanks to Professor Landsberger for his time and for helping us tremendously with our senior design project. We can now take your questions if you have any, and thank you for your time.